Uh, Good morning. I'm Professor Ashish Juneja from IIT Bombay, and I welcome you all. The Geotechnical Engineering Division at IIT Bombay, in association with Indian Geotechnical Society Mumbai chapter, is proud to host the first webinar on mitigation of rockfall geohazards. This webinar is part of the series on rockfall hazard and mitigation for lifeline systems. We plan to host a selected few webinars on this important topic, which will be spread over the next few weeks in August and September. All these online seminars will be delivered by specialist engineers, consultants, and academicians. And we will share these details in due course with you all. The recent Kinnaur rockfall in Himachal Pradesh, in fact, just 4 days back, it has shown that how dangerous these rockfall events can be when these fast-moving rock and earth fall, they bounce or roll off from a cliff or down a very steep slope. They have caused personal injury, loss of life. There is serious damage to building and structures, vehicles and highways in their path. In fact, these events, these catastrophic events, they occur without warning, and it makes it difficult to predict. Many times it's difficult to predict how and when they can occur. These incidents are very common, and they are common occurrence in the Western Ghats, very close to us. They have affected the Central Railways and the Mumbai-Pune Express Highway. Today, we are very pleased and honored to have Mr. Giorgio Giachetti of Alpigeo Consultants, Italy, as our speaker for today. Mr. Giorgio graduated as a mining surveyor and geological science. He has more than 34 years of experience as consultant for public administrations, private companies, contractors in the field of the rock mechanics applied to the rock slope stability and tunnels. He has designed countless rockfall protection installations using both meshes and barriers, and he has a comprehensive experience of the practical and theoretical aspects of rockfall protection system. He's also carried out numerous studies which concern application of meshes as flexible structures facing for soil nail and for rockfall, the debris flow protection system. His work has been carried out mainly in Italy, even if his experience as a consultant, which has ranged from Australia to Latin America and India and US. He is a member of the European Working Groups for the Standard EN 14490, that is the execution of special geotechnical works, soil nailing. He is also a member of the Italian standards UNI 11211, which is on rockfall protection measures, and UNI 11437, which is on test and measures for slope coverage. He has been a lecturer in several seminars for professional associations, administrations, and universities. He has written several papers which concern mesh and barrier protection system against rockfall, debris, and landslide. Now, before I hand over the floor to Giorgio, just 1 second, please. Yeah. Now, before I hand over the floor to Giorgio, there are just three important announcements I wish to make. The first is, please feel free to post your questions on either chat window or the Q&A window. That's right at the bottom of your screen, bottom right, I believe, during this webinar. So the speaker will take these questions in between and towards the end of the webinar. A link to the feedback form will be pasted on chat window soon. It will be pasted again during the seminar. So you're requested to spend few minutes to fill this form when this webinar ends. This feedback form also has a question whether you would like to have a certificate of participation. Please type in yes in this form. In that case, an e-certificate will be emailed to you in the next few days. Now invite our very special speaker, Mr. Giorgio, to take the floor. So Giorgio, please.
Yeah. Okay, you should see my screen, isn't it?
Yes, yes,
Okay.
very clear.
Okay. Good morning, first of all, and thanks, especially thanks to the Geotechnical Engineering Division of the Department, Civil Engineering, and Indian Geotechnical Society to invite me to this speech. And special thanks also to Professor Ashish Jumeja. I'm honored of this. Okay, now, which is the goal of of my presentation is mitigation of rockfall geohazard. This will be a general speech. A general speech. I don't go deeply in the matter for the calculation system and so on. So there will be no formula in this speech. First step, which is the goal of our presentation. We already said this. And the first idea I want to put in this discussion is that the geohazard is like the seismic hazard, exactly like that one. We know that it will happen for sure, but we don't know when and how big it will be. Sometimes it will be very small. We don't care about it usually, even if it is always dangerous, but sometimes it is a disaster, as we can see in this picture. In a certain way, we know where, but we don't know when it will happen. Topics of this presentation: the overview, in which where I will explain very roughly the main topics for the rockfall protection, and after that some issue about the intervention in the detachment area, the intervention far from the detachment area, that is barriers. In this second case, in the first case, on the detachment area meshes. And after that, we will see factors of design. One technical issue, when the pop-up windows appears, do you see these, the pop-up of my screen?
Sorry?
Sometimes it appears that a new participant, like here, do you see the pop-up windows?
Yes, that's my job. I'm actually making them enter. So please request you to ignore that because you are now the co-host. So you also see this. Sorry for
Okay,
that.
but you don't see that.
No, I see this, and I'm actually doing this, making them enter.
Okay. Okay, I go on.
Yes.
First, overview, which is the issue. We go to see the main methods. Maybe many of you already know these, so I ask your patience because you already know. First method is quite simple. It looks simple. Is the scaling or trimming or reshaping of the slope. Scaling is a basic operation, a basic job to develop on the slope face for several reasons. First, because it put in a minimum condition of safety for the workers, the slope. Before to go down on the slope and put meshes, we have to clean the slope and put it in safe condition. Specialized workers are required for this. Rockfall barriers is another type of intervention. Type of intervention typically developed at the toe of the slope, far away from the detachment area. When it is not possible to do intervention in the detachment area, for several reasons, we install a rockfall barrier, like the one you see in the picture. A similar solution to the rockfall barriers are the embankments. They are installed as well on the bottom of the slope, far away from the detachment area. But the solution is the same, and the calculation approach is more or less the same. After, we have to another family, another group of solution, which is the simple drapery, that is a mesh applied on the slope without anchors. Anchors are applied only at the top. So the main components in this case are drapery and the top longitudinal rope and the top anchors. These are the main components. After that, we can insert some intermediate rope, or at the bottom another rope, and so on. But obviously, we can apply this type of intervention on the detachment area. Let me say, mainly on the detachment area. Sometimes we can apply it also in a different position. For instance, where there is the run-out zone with a lot of debris, we can apply it also in that position. This is an example of simple drapery. As you can see, the simple drapery is a quite effective solution, fit to catch debris of large size. Some block in this slide you can see some blocks has a diameter more or less close to 1 meter. But most frequently they are used for small blocks. Moreover, we have secured drapery. What is the secured drapery? Is like the simple drapery plus a pattern of anchors which stabilize the slope in cooperation with the mesh. So the main components are meshes, anchors, cable netting. This type of installation is done on the detachment area and can be used on a rock face typically, but also on soil slope, steep soil slope, like soil nailing. We will see which are the main steps for the calculation without go into the problem. This is the typical installation. As you can see, we have mesh, the raster of anchors, and additionally also in this picture we see there is the cable netting overlapped on the mesh. This cable netting is very useful, really helps the effectiveness of the intervention because it keeps down the mesh, and distribute the forces from the mesh, transfer the forces from the mesh to the anchors. But we have the opportunity to speak in a better way now. Second issue on the detachment area. Now we go deep on the meshes. I don't go too much deep because it is quite long, but just an overview. We have meshes and anchors all together. Meshes and anchors means they have to cooperate, and this is a problem. We have to understand how to calculate this type of cooperation. First, we have to say which type of anchors we are using. Typically, on the rock face are used tie-back anchors, like this one, bolts, or nails, dowels, anchors. The name could be different. But anyway, which is the difference between these? The tie-back anchors transfer the forces from the head here down to the foundation. And this segment is free, and it transfers the forces from head to down. The same is the bolts, but the foundation is very small, and the foundation can be slightly tightened, and after that the bolt can be grouted. Usually in the rock face, for the intervention we do for practical reason, and let me say also for effectiveness of the solution, we use this type of intervention. In this type of intervention, we have the head with the plate, but the foundation is a continuous. The steel bar is grouted for its entire length. So in this case, we cannot pre-stress the anchor. And this means this is a totally passive solution. Here we have active solution on the tie-back and bolts. We have active because they develop force before the displacement take place. In this case, no. The displacement take place, and after that, the nail can develop a force as a reaction. Well, this definition is typically from is taken from the sort of let me say Bible of the rock mechanics from Eke Brown, that says the anchors cannot be tensioned, and hence must be installed before significant deformation of rock mass has taken place. So, I repeat, we are working with totally passive intervention. What does it mean, passive? Means that even if we, in a certain way, pre-stress the anchor, that is, we screw down the nut on the plate, we don't develop this type of pressure. It's impossible. Basically, we do a short circuit of the forces, and no pressure is developed on the sliding plane. What type of anchors are used? There are a lot of anchors on the market, but the most important feature is they are corrugated. Don't use if you have to do some work, don't use smooth surface. Why? Because they don't have significant resistance to the pull-out stress. And after that, we can also see that there are different type of corrosion. This is black steel, these two. This is with with resin, and these are with zinc coating. In the market, usually we use these two type, black one, but sometimes in special condition we use with resin, or frequently also with zinc. Well, concerning the shape of the section, we have solid bar, and also in this case hollow bar. Usually this type of hollow bars are used for the soil nailing operation, not in rock, even if they can be used also in rock, but usually we use solid bar. The calculation of the solid bar is done considering also a crown of corrosion. Let me say 2 mm, 2 millimeters, just to take in account that there will be in the lifetime of the bar a reduction of its resistance on the tracks where there is water circulation. In which way is done the grouting? The grouting is done directly by means of a pipe that reach the bottom of the hole, and the grout rise into the hole up to the mouth of the hole. And usually the grout is made with cement and water. The ratio between cement and water is more or less in weight 0.5. There is also some additive for increase the resistance, increase the resistance of the cement and prevent the shrinkage of the cement, of the grout. Also can be used resin. Okay, in which way the anchors can work? I show this, first of all, this sketch. In this sketch, you see the line perpendicular to the sliding surface. So when we have the anchor placed parallel to the perpendicular line, this anchor will work in pure shear condition. If we incline the anchors, that is, we increase this angle, step by step, the anchor works in pull-out condition, in tensile condition. If I look on this sketch, this block, this anchor D will work in pure tensile condition. On the opposite condition, we have A anchor that will work in pure shear condition. After that, we have a lot of intermediate condition. How can we represent this on a diagram? Here we have the, the force on the y-axis, the force developed by the anchor on the joint, that is the stabilizing contribution of the anchor, and here the angle theta. Theta is this angle, okay, from 0, that is pure shear condition, and here 70 degrees up, sorry, 70 degrees. 70 degrees means the anchor is placed down in this position, and it works basically on almost basically in tensile condition. And you see the shear condition, the stabilizing contribution of the anchor is quite small, but it increases, it grows step by step when we move towards the tensile condition. We have the blue line and red line. This blue and red line depends, the position, the static position depends on the roughness of the slope. Roughness of the slope means dilatancy of the joint, and when we have large dilatancy, the work of the anchor, that is the stabilizing contribution, is higher, absolutely higher. This anchor, this graphic is calculated in according to several authors, and basically Panet, with a quite famous formula. Meshes. We have several types of meshes. We know that the meshes have to catch what is moving among the raster of anchors. We have to watch what really happens in the field. In the field, we see that even if we put in contact the mesh on the ground, on the surface, there will be always space, always space between mesh, the plane of the mesh, and the surface. There will be always, and moreover, we can lift easily the mesh, even if it is a quite strong mesh or very strong mesh, we can always lift the mesh. There is no problem to lifting. That is, the experience says, and the physics also says, that the mesh can only, it is a membrane applied on the ground surface. The mesh can only develop tangential forces. No one force can be developed by the mesh perpendicularly to the ground surface. In other terms, if we do, if we put the anchor down in a depression, in a convexity of the ground, we can create a sort of dome, let me say dome here, that from the theoretical point of view can develop forces at pressure. But in reality, what happens? Because we have a large, very large deformability of the mesh, then this force will be negligible, absolutely negligible. And if you go on this position and try to lift the mesh, with the hands, you can do it. You can lift it. How can we know the properties of the meshes? With tests. Basically, there is the test UNI, is an Italian standard, and also the test ISO, another standard. These tests ISO and UNI are equivalent. This test, in this case, is aimed at verify the deformability of the mesh under punch condition. There is a shield that punch on the perpendicularly to the screen, to the mesh plane, and it move on the plane up to the plane of the mesh up to the mesh is broken. This picture is a courtesy of McAferry, which has developed a lot of tests on the products on this. Just to give you the idea about the laboratory punch test, the results of the laboratory punch test, we have here some type of mesh, for instance, steel grid. This is equivalent to a double twist wire mesh. This is mesh, a double twist with reinforced with cable, HA panel, cable panel, from small size of the panel of the square, 250 up to 400 mm diameter, 8 millimeter rope, and ring net, the strongest mesh. We have a different range of forces of resistance to the punch test. The range goes from 82 kilonewton to 820 kilonewton, and the deformation ranges from 0.24 mm in the case of the HA panel. They have a membrane stiffness up to 1.5 meter in the rupture condition, that is 800 in the case of the ring net. Which is the test? We go one step back. The test is made on a sample 3 by 3 meters. This sample is 3 by 3. It is fixed on a square frame by means of a stiff system. In this case, you see cables, but they are basically stiff, not perfect stiffness, but they are stiff. Okay. And the test is done moving the shield, which has a diameter of 1.5 meter. In this case, it is a small one, but according to the standard is 1.5 meter. And the test moves the shield with a velocity of 2 mm per second. Okay, after that, another important property of the mesh is the tensile resistance. There are several standards for this type of test. Standard UNI and as well as ISO, they are quite similar. Which is the resistance, tensile resistance. I don't go deeply in this matter, but it could be very interesting understanding the way, the procedure of testing in order to understand also the limit of each test. Anyway, we see that the range of meshes going from basically, this is a double twist, reinforced with the cable, has a resistance of 60 kilonewton per meter, per meter. This is wrong, is missing the meter. And HR30 with cable, the cable of reinforcing are inserted every 30 centimeters. The tensile resistance is 177, almost 180 kilonewton per linear meter. H panel. The H panel is their panel made with cable, square, with a mesh square, rhomboedral mesh, 200 by 250 by 250, and as already I said before, up to 400 by 400. The tensile resistance has a good range from 140 up to 250. And finally, the ring net has a huge tensile resistance. Well, secured drapery on rock face. The secured drapery requires a certain stiffness and flexibility in the meanwhile. Why flexibility and stiffness? We have to think that the mesh would be like the shotcrete, but it is impossible. The shotcrete is stiff, very stiff, whereas the mesh is flexible. But if we have a very stiff mesh like the shotcrete, it is impossible to apply the mesh on the field, on the ground, on the surface of the slope, which is very uneven. So on one hand, we want something of rigid membrane stiffness. On the other hand, we want something of flexible, that is something which is well fit on the slope face. And these two properties are not cannot be combined. And this is a very interesting product because it combines a certain flexibility with a certain stiffness and tensile resistance and punch resistance. The product has different spacing between the cable, and so can be applied on each type of slope. On each type of slope that have small blocks as well as large blocks, depending on the spacing between the cables that give different properties. Well, this is an application on the slope, and application on the slope of a mesh, in this case steel grid, with a pattern of anchors. Which is the logic we have to use to calculate the cooperation between anchors and mesh? This is the question. Now, the logic is is that we should use a finite element method analysis because we have different type of object that cooperate together. But the use of this approach is basically a nonsense in the slope, because we don't have time to develop the calculation. We don't have enough information. Many times we are forced to develop in an emergency situation a quick solution. So we have to use limit, equilibrium, or analytical method. And this is the sketch that gives the idea of this approach, analytical approach. First of all, imagine that on the slope there is a portion of weathered rock, and the goal of our intervention is to, let me say, consolidate or stabilize, prevent the sliding of this unstable portion. If we insert a raster of anchor, we know that the anchors have to stabilize the whole superficial portion. And the mesh has to catch what can move, what come out among the anchors. So they have different purposes, the whole slope anchors, and the small portion, the mesh. With this approach, we can understand which is let me say, the forces against the mesh, and the forces against the anchor, and after that combine the two forces, taking account of the resistance that we know on the base of the lab test. In order to explain all the passage of this calculation, it take, I say, some hours, and we cannot go deeply on the matter. After that, we go very quickly on the simple drapery. Simple drapery means, we have seen, simple drapery means mesh applied on the slope. In this case is a mesh plus mat, anti-erosion mat. The calculation principle is this. We have the mesh on the slope, and the mesh keep stabilized at the bottom portion of debris. So the anchor on the top has to keep the weight developed by the mesh itself and the pocket of debris at the bottom. Plus, if there is the condition, I think in some place in Himalaya, there is also the snow. There is a layer of snow here. And so at the end, we have that the anchors have to hold, to keep stabilize all these portion, and the mesh also has to stabilize these forces, load of debris plus load of snow plus weight of the mesh itself, and the tensile resistance of the mesh must be greater than these loads. This is the principle of calculation. Well, the problem is always to understand which is the thickness of the unstable portion. Thickness is 1 meter, 1 centimeter, half a meter, which is the thickness. In order to understand this, we have to work on the slope, or better, we have to watch, if it is not possible to work, watch the debris at the bottom in order to understand which is this size. This size. Watching on the slope based on the spacing between the cracks between the joints, more or less we can understand the portion, or looking at the attachment niches, we can understand the thickness. But usually it is easier watching at the bottom. Some cases just to understand. Here we have a thin layered limestone slope. And okay, which is the size of the blocks? But usually it is related to the head of these layers that move out, and the thickness is maximum 0.1, 0.2 meters. If there are large blocks like this one, we know that these blocks must be scaled, or here we have to reshape the slope. So the mesh cannot take in account of this. The mesh is not aimed to catch this. Another situation. In this case, we have several blocks, small portion of blocks. We are in front of the sea. This is the Indian Ocean. We have several blocks, very, very small, but also large blocks, especially on the crest of this cliff, small cliff. We have blocks that have a dimension, a size 0.3, 0.4 meters. Just to give you the idea of the problem. Here we are in an Indian cliff in center of India, and the size of the blocks is quite large. Quite large means they have a size of 0.5, 0.6 meter, and we can recognize also the pattern of joints and based on the pattern of joints, also the detachment zone of these blocks. Here we can foresee also the next or the most dangerous portion to be consolidated quite easily. In this case, with this type of thickness, this size of blocks, the anchors start to be very, very important, because the mesh cannot stabilize itself. The mesh cannot stabilize this type of blocks. The anchors are absolutely necessary. Well, we can recognize also different condition. In this case, we have toppling, some toppling and sliding of the joints. So the prevention or the control of this type of instability is very, very problematic. And I repeat, anchors are always needed in this condition. Another matter, another matter, I mean, another type of problem. Here we are always in some Indian, I don't remember, to be honest, which one, Indian highway. And as you can see, in the picture is not clear, but there is a large crack, a sequence of cracks that give the chance to collapse this portion. The size of the blocks is very, very large. We are speaking of 3-4 meters by a couple of meters, so the blocks are not at all small. We can operate with the meshes in this condition just for the small blocks, just for these, not for the large obsolete. And moreover, if we want to stabilize this slope, we have to reshape, first of all, and after that to operate with deep anchors in order to stabilize the large blocks which have a size of several cubic meters, and after that apply the mesh. So the larger the blocks, the more complicated is the solution. We have always to keep in mind the limits of our possibility with meshes. Thickness, in this case, we have a type of rock like fleche, that is a rock with sandstone and limestone, weak limestone or claystone. The weathering is quite large, especially close to the crest zone. In this case, the solution is difficult because we have associated two types of rocks. The association of two types of rocks means that the mesh has to keep the large block as well the small debris. And so there is the risk of breakage of the mesh because dynamic effect due to the large blocks, and in the meanwhile also the load related to the small pocket of debris. This situation is typically in the first, I think, to the Himalayan situation. In the first mountain we meet going in the Himalayan region, where before the metamorphic zone, we have this type of rock formation. Well, how can what we have to do on site? We have to do a simple sketch. Now there is LiDAR survey. The possibility are very, very interesting. Automatic survey, geological survey, in order to have the raster of joints and understand which are the weakest portion of the slope. But many times it's enough to go on slope, walk at the bottom of the slope and take some measure, quick measure, in order to have the idea of the intervention we have to install. For instance, because we have a slope with, let me say, these are 40 meters, and in this portion of the slope we have large blocks. We need in this portion strong mesh, whereas in the other portion is enough a very simple, let me say, double twist wire mesh. Maybe we can also note that there is a channel. With the channel, we have the risk of debris flow because we see the sign on the sea, the effect of the debris flow on the riverbed, and we recognize that there is this risk. We can foresee also a specific solution for debris flow and so on. This is a sketch, a field sketch that gives you the idea of the sensitivity we have, we need to have on the field. Okay, I think if there is any question, we can shortly stop and answer. Otherwise, I go ahead.
Yeah. Okay. There are, in fact, Giorgio, two questions.
Yeah.
Okay. I'll just pull them up. I can read them for you.
Yes.
Second, please. Yeah. So the first one is by Mr. Gaurav. I think this question was when you were presenting about the grouting, the grout which went in. So the question was, how much pressure is generally used for the grout?
Yes.
Okay, that is the first question.
Yes. I answer now.
Yes, yes.
Okay. Usually there is no pressure because they are short. They are no pressure is only the pressure of the fluid. Only gravity. They are not in pressure with, let me say, 1 atmosphere or MPa of pressure. No, nothing. Only gravity. The gravity is on the pipe, and the problem, the grout is completed when the cement come up on the mouth of the hole. That is all.
Yeah, yes. Okay, yes. So the second question is from Mr. Mayuresh Bukhare. He has appreciated this your presentation. He says very informative presentation. He says he has a doubt. It says the doubt is regarding the design life of rock slope protection work. He says, does the weathering of the rock, which is a continuous process, also limit the design life of this slope protection work for the current state? So if you have a design for the current state, does the over designing takes into account the future depth of weathering if possible? So if so, how
Yes.
can one judge the future depth of weathering?
Yes. The answer, this is a very good question. I didn't say, but we see in the next slide, it didn't say about this problem. Let me say of the weathering. Typically, we have to foresee that there are rock that release in the time small quantity of blocks, typically the mudstone, but there are rocks that in the time release a lot of debris, typically the rocks with high contents of clay. This is the case in this picture. You see this case, high contents of clay. And this means, in this case, a lot of maintenance. We have to foresee that in our design, there is maintenance. No other chance. How can we minimize the maintenance? What does mean maintenance? I can show, I can speak of this specific case. Here, the road authority every 2 years open the mesh, release the rope, the raster of the net of rope, and let the material, the debris, fall down. They clean the material at the bottom, and after that, reinstall the mesh and as it was in the design condition. Obviously, every year, the anchor are a little bit more out. The head of the anchor is a little bit more out, far away from the surface because there is the erosion. And the foundation of the anchors is year by year, time by time, shorter. So in this case, we have to foresee longer, deeper anchors in order to prevent the problem of re-drill, reinstall all the anchor pattern. Anyway, this is a little trick, but doesn't solve the problem of the maintenance. We have to do maintenance. On some rock, like this one, the maintenance is quite heavy, is frequent. In other rock, is not so frequent.
Yeah. Okay, so there are in fact three more questions. You want to take them now or maybe towards the end?
We can go at the end.
Okay.
Go. How long? How time is it available? Still available?
It depends upon the patience of the audience. So,
I go fast.
yeah, so in case the number of participants reduce drastically, I think it will be the time to stop. But
Okay.
now it's still okay. People still have patience.
Okay. Very quickly. Barriers. Very, very quickly. The barriers have to catch energy, not force, energy. What is the energy? The energy depends on the velocity and on the mass. To give you the idea, a projectile has with 100 kg, with a velocity of 180 meters per second, gives an energy of 1,600 kilojoules. A truck moving with 26 ton, moving with a speed of 19 meter per second, 70 kilometers per hour, give 5,000, more or less, 5,000 kilojoule. Usain Bolt, we can say, has an energy of maximum 4 kilojoule. To give you the idea, with a speed of 90 kilometers per hour, a mass 16 ton gives 5,000 kilojoule, 10 tons, 3,000 kilojoule with a free fall of 31 meters. Well, how we know the barrier? We know the barrier because the barrier are tested with crash test. The crash test gave us the capacity of the barrier in terms of energy, residual height, deflection. Deflection means which is the elongation of the barrier after the impact. Forces on the anchors, and let me say there is one additional information, behavior of the barrier on the maximum energy level and behavior of the barrier on the service energy level. Service energy level is the barrier stressed with 1/3 of the maximum energy level. The maximum energy level is the maximum capacity of the barrier. 1 kilojoule more, and the barrier is not able, is not fit to catch the block. I go with very, very fast information. This is the barrier before and after the impact. This is the nominal height of the barrier, and this is the residual height of the barrier. After the impact, we have the residual height of the barrier because the barrier deforms. Okay, there are several certified barriers. I skip this, and we go on the embankments. The embankments are like a barrier, but they have a different behavior. They are fit to resist to large impact, very, very large impact, without deflection like the barrier. So you have here the idea of the blocks, which is the difference between barrier and embankments. Here you see the difference. This is the shape of the embankments. The embankment has a deflection close to zero, few centimeters. Here on the upslope face, some decimeter, but basically zero deflection. The barrier has a large deflection because there is the deflection due to the deformation of the mesh. So the final space required from the barrier is this, from this position down to this position, whereas the embankment takes this. Moreover, the embankment has a capacity, let me say, there is no limit, but personally, I have experienced up to 50 megajoule of energy for multiple impacts. That is first impact, second impact, third impact without problem. The barriers has at the present energy, maximum energy, 10 megajoule for one single impact. So the embankment is absolutely better than the barrier. Which is the problem? The embankment requires a foundation. And so, if there is no room for the foundation, we have to install a barrier. Or the slope is too much steep, we have to install a barrier. I ran down to the factor of design. How to take the decision. Sometimes it's not at all easy to take a decision about the barrier, sorry, the best solution we have to install. First, we have to do a good geological survey, good geomechanical survey in order to acquire information about the slope. It is obsolete. It is obvious. Nothing of new. But sometimes is not so clear. Why I say this? Because there are several types of instability. And for each type of instability, we have different type of solution. Here, for instance, double twist wire mesh is enough. Here, panel, cable panel, HA panel would be enough. Here, more anchor, strong mesh like panel. In this case, imagine a very large height slope, let me say 20 meters in this situation. We need deep anchor. We have to stabilize the entire slope. Mesh. Yes, we have to apply mesh, but the mesh can catch only the thin, small portion. This is not a solution for mesh, evident, no? This is a problem for deep anchor and deep stability. Maybe tie-back anchor. Sometimes we have very big, very large blocks. In this case, no anchor, no tieback, no mesh, nothing. This is not a problem. This is a data. A data that is, we have to accept is as it is. Stop. Especially if the detachment zone is far away on the slope. We have to consider the national reference. I know there is some standard in India, but I didn't find it. Sorry. Slope morphology. This is a very important factor because on the slope morphology depends the solution. Just to give you the idea, here we have a crest. Here at the bottom we have a valley, one road. In this case, it is easier to put a mesh here because with a mesh on this crest, I solve the problem for a long section of road. Here we have other cliff. In this case, I have to put a barrier because with a barrier in this portion of road, I put in safe condition the road from rock that come down from a large, wide portion of slope. So the morphology is very important. Obviously, the morphology is important also for the shape, for other type of shape, and maybe later on we see some information. After that, how to choose the solution. We have to take in account the risk, let me say, the frequency of the events. In a slope, we have a lot of small blocks that can generate damage on the road. And one very large blocks. Okay, the frequency of falling is 90% is related to the small blocks. One block only give 10% of risk. Okay, if I insert a solution just for the small blocks, I preserve the road from the 90% of the risk. That is, if I insert a barrier for small blocks, in this case, I save the road. Maybe when I have money, I can do an intervention, a specific intervention for this one also. Speaking of money, we imagine to have a slope, with a certain height, and I have two opportunities to insert a barrier. Let me say, can I insert the barrier here, or better I insert the mesh on the whole slope? The answer is this. This is the slope height, and here we have the cost of intervention per linear meter of road. If I insert mesh, the higher, this is the line related, let me say the green line is related to the mesh, the cost of the mesh. The higher the slope, the higher the cost. Obviously, if I insert a very expensive mesh, this is the cost. Simple drapery, no anchors, the cost is small. But anyway, if I insert a barrier on the slope for the protection of the slope, the cost doesn't change. The cost is always the same. So if I compare a slope 60, 50 meter height with this type of intervention, okay, we have the cost of the intervention here, but we know that if the slope is 60 meters, start to be cheaper the intervention with the barrier. This is the concept of risk. obviously we have to consider the risk in the slope. What does it mean, risk? In this case, the best solution is clean, put down, but we cannot put down here because there is a refinery, petrol refinery, so is a problem. The big mistake was done by these people that built the industry, just the factory just here. Okay. Just to say the problem of the performances of the barrier. If we are in this situation, we put barrier that this situation above the portal of a tunnel. Portal of the tunnel is quite delicate position because the people cannot come out of the tunnel and suddenly find a block on the road. So we must be safe. And in this condition, no maintenance is possible, or we have to reduce absolutely the maintenance of the barrier. In this condition, we have to use a barrier that works with its service energy level. That is, we have to use an oversized barrier in order to reduce its maintenance. But if we have a risk, a situation where the risk is well accepted, typically mining area, we can use easily a barrier that works with its maximum energy level. In this way, I minimize the cost per units of energy. Let me say, I can catch the block and I don't care if the barrier is destroyed or less, or non-destroyed, because to me it's not a problem, the maintenance. I can do easily it in this situation. Other matter, very, very quickly. Depending on the type of intervention, the cost is different in the time. This depends. We have to consider the maintenance. In the y-axis we have money. X-axis we have years. Think to three different type of installation. Rockfall barrier. This is the graphic of the life of a rockfall barrier, which has an efficiency of 95%. The graphic of the life of an half tunnel, a canopy for the protection of the road, same road, okay. Efficiency 99%, and finally embankment. Embankment has a low cost and low maintenance cost. Barrier has a very low cost, and maintenance in the time could be very large. Embankment has a huge initial cost, but in the time low, very low cost and higher efficiency. So these graphics says us that depending on the perspective we are facing with, we have to choose different, we should choose different solution. Barrier or embankment or half tunnel. Other matter concerning the maintenance, we have to do to watch at the performances of the barriers and of the material, more generally speaking. That is there any problem of rusting? Rusting means less efficiency in a short time. We have to pretend that the material give a good performance against the corrosion. Environmental problem. Some product can be well adapted on the slope, just to show this example. well adapted in order to preserve trees or nests and so on. Last but not least, there are several other questions. The skilling of the contractor, of the workers. It is totally useless to foresee to develop a good project if at the end there is no contractor able to develop it. Able means that the contractor must have skilled workers able to work in good condition, in safe condition on the slope. Other matter, preliminary works, we already said something. I skipped this in order to be faster. The organization of the work yard. Organization of the work yard is very important. The first question is, how can I reach the top of the slope? Have I an access road at the top, at the bottom? Can I use the crane? Can I use the helicopter? The helicopter is basic, a basic transport method for this type of intervention. But rarely I saw in India, for instance, this type of application. This picture has been taken in Saptashringi temple area, where the barrier have been installed with helicopter. There is the crane just to prepare the field, but the transportation on the field, on the slope by means of helicopter. Platform to drilling. Can we use the platform, or have we people able to work in a suspended platform or directly suspended on the rope? Finally, we must be realistic. Don't get confused in the race rule. What is the race rules? I know we are on the slope. We have to design. We want to know exactly which is the roughness of the joint, the spacing of the joint, length, gap, and so on. Everything, compression of the resistance of the rock, and so on. Many times we don't have time to do this, and moreover, we don't have enough information to develop a good geological model, a geotechnical model, which is the Ray rule. Measure with a micrometer, mark with a chalk, and cut with an axe. We, at the end, we are forced to cut with an axe. So all the process of the design must be realistic. We have to remember that we have to cut with an axe. I know I'm quite rough to say this, but many times we are speaking of very cheap intervention. We are speaking of sufficient intervention where our precision is not so required. And how to develop the design? We have action resistance. We know that with the intervention, with our intervention, the equilibrium between driving forces and reaction, resisting forces, at the end, when we insert the intervention, should be the safety factor 1.5. And how can we do the analysis? We can develop the analysis in back analysis. That is, we know that at the present, the safety factor is at least 1 no 0.5, 0.1. It is 1 because the slope is still there. Doesn't exist this situation. If we have this situation, we have done a bad geomechanical model. Okay, final remark, we have to remember that a good intervention cannot be cheap, good, and fast altogether. And this intersection zone doesn't exist. We have a good intervention and cheap, it will arrive too late. If it is cheap and fast, it will be ugly, and good and fast will be expensive. Free basically doesn't exist, or it is garbage. Okay, this is my final slide. Thanks for your attention.
Thank you, Mr. Giorgio. Thank you so much for your wonderful presentation. There are just few questions which I see.
Yeah.
I think the questions I see them to be grouped into two. So I'll just take up the first set. It's in fact a single question. It's from Kiran Gadi, I think. Yes. So she she has asked, in fact, on a question on your HEA panel mesh. So there was a slide sometime, I think around just some time back, you showed a table with a HEA panel mesh of 250 by 250 by 8 mm diameter. And there was another one which was 300 by 300 by 10 mm diameter. So the 250, 258 was giving a strength of 200 kilonewton. Yes, I think that, yeah. So 250, 258 is 200 strength under punch. And the other one, where is it? Just another one is 300, 310. Yeah, it's giving 150, is it? So that's giving 140.
Yeah, you mean punch these?
No, I think the question is on numbers. So numbers which were 300, 310 is 140. I see this.
40.
And the 250, 258 is 200. Yeah, this one, I think. This one.
Yes. This depends on the density of the rope, because 200 by 200 means higher density of rope. And that is 200 by 200, 250, 250 is, if I correctly understand the question, is absolutely has a larger density of rope, number of rope per linear meter. That is the focus.
Okay, so with 250, 258, you have more rope density. That is why the deformation, the punch deformation is more. Yes, I understand now. And 300, 300, you have less.
See,
Although
this
it
is
appears as if you are using a 10 mm, sorry, you're using a 10 mm diameter rope, and the 10 mm is giving less strength. That's what I think the appearance seemed to be.
Yes.
Okay. Okay. The other question is, in fact, there are from three people, but I believe all three are from the weathering point of view. It's something similar which has been asked some time back. So I'll just club them together, I think, just to put them together. One is from Mr. Jitendra. The other one, I don't have a name. They're just an admin. And I think there's a third one. I'm just trying to catch the third name. Just, where is it? Yeah, third one I think is again from Rakesh Kumar. So the question in a sense is on weathering. So the Jitendra says, what is the periodic maintenance or the monitoring required after installation of the mesh? What Rakesh Kumar has asked is, as the time passes, the morphology of the rock will change as it weathers into smaller pebble due to pressure and temperature effects. So I think the question is similar to before, but it says because then it'll pass through the mesh hole, and it'll be small pebbles, small pieces can pass through the mesh hole.
Yes.
Make sure.
First of all, meshes are not a continuous surface. They are not a tissue. They have large holes. Large holes means some blocks can pass down. Absolutely. This is, let me say, a small problem, but there is. If we have to protect in specific condition some very, very important zone. Let me say we are just above with an overhanging slope. We have to protect the house just below the overhanging zone. We have to insert a different type of mesh with, in some case, we have inserted 2 mm mesh. To show you in this case, in this slide. Okay, here we have double twist wire mesh plus another mesh, very thin, because just below here there is a path for tourists in a very frequented area, touristic area, very important. So we had to protect. We did, the client asked us to insert this double mesh. This is just for example. Concerning the weathering, I say basically it is a problem of experience on the local climatic condition and local type of rock, outcrops of rock, and we have to watch the rock. I can say only that in order to understand which is the limit of capacity of the mesh in that specific environmental condition, we have to watch which is the displacement of the mesh, under load when there is the pocket of debris. Just to give you the idea, I show this picture. Okay, good. This in this type of test. In this type of test, we verify which is the displacement under load, a specific load. Okay, but we know the behavior of the mesh when it is loaded by the pocket of debris. So the design has to foresee which is the maximum acceptable displacement admitted by a specific type of mesh. If we know this, when we reach, we can see, we can watch the slope and this type of displacement due to the pocket of debris, then we can measure it and say, okay, the displacement is close to alpha meter. We have to do maintenance. This is the correct process. In front to this type of problem.
Yeah, so there is just I think one more question if you can take. It's something I think you had presented a very nice a figure to show wherein you would like to use a flexible barrier and a drapery system. I think a rigid control system. This question is from Bhim Yadav.
This one?
I think there was a table which showed the cost factor. I think this is also there. Yes, the same. I mean, this question would be in mind of many people. Wherein to use? Yes, this one, please. This was the figure.
Yes. As you see, there is no unit of measure here. It is money per meter. But you have to think. The approach is this. You go on site and the client asks, please protect the road from this slope that release blocks. You have two possibilities, okay? Mesh, cover all the slope with mesh, and insert a barrier. Now, the cost of a barrier is, let me say, I'm speaking of euro or dollars, but could be $1,000 per linear meter. Okay, 1 meter of barrier. You have to compare this with the height of the slope. If I have to cover the entire slope with a mesh, the cost, the incidence of the cost is, let me say, $100 per square meter. I invent, okay? The slope is 100 meter the height. You have a huge cost per linear meter, no? You have 100 times 100. You have $10,000 per linear meter due to the mesh. It is absolutely cheaper. It is a local evaluation. Is not you have, let me say, to use this type of approach, this type of graphic, by inserting the right type of barrier and the right cost you have in your mind. By a right energy level of barrier, because this is a high energy barrier and this is a low energy barrier. The low energy barrier costs less than the high energy barrier. So you have to go on site and compare.
Yeah, thank you. So I think that's all. This I don't see any more question. But if there are any, I request the participant to email this to either Giorgio or to me, and probably Giorgio will be kind enough to answer them.
Yeah.
Yeah. Okay, so I think we are at the end of the road. You've taken a lot of your time, early morning time.